We're moving on to chapter 10, and in chapter 10, we're going to stop talking about gases directly for quite a bit. And instead, we're going to talk more about the other two primary phases of matter that we encounter in our everyday lives, which are chemicals in the form of solids and chemicals in the form of liquids. Specifically in this chapter, we want to talk a lot about why it takes energy to convert a solid to a liquid and a liquid to a gas, and the role that intermolecular forces play in holding molecules together. In this chapter, we're going to primarily talk about intermolecular forces in the sense of how does the strength of intermolecular forces affect melting point and boiling point, right? What temperature matter, a specific type of matter, a specific chemical converts from a solid to a liquid. But this is kind of a deceptively simple treatment because the same considerations of the strength of intermolecular forces, the attractive forces that hold molecules together in solids and liquids, has a lot to do with some of the most elegant chemistry that happens in the real world, some of the most important environmental chemical reactions, particularly those that happen in water, and particularly chemical reactions that happen in biological systems. So DNA replication, the way enzymes release energy in your body, the way your immune system protects you from disease, all come down to three-dimensional arrangements of molecules and how molecules on the surface of biological structures or complex biomolecules like proteins or nucleic acids inside of cells interact with one another is all understood through this lens of how is the molecule shaped and what are the intermolecular forces like. So we're going to start this off with kind of what may seem like kind of a blunt treatment of the molecule looks like this, therefore its intermolecular forces are these, therefore its boiling point is this, therefore its melting point is this. But these same types of intermolecular force considerations are responsible for explaining very delicate biochemical phenomena as well, like why specific nucleic acids inside of a DNA strand only recognize their complement, and why DNA has that beautiful double helix structure. So just to refresh, going back kind of the kinetic molecular theory of gases and thinking about what states of matter look like, I really want to reinforce in your mind the particle cartoon visual of the states of matter, right? Where solids are ordered and densely packed, and the particles, the molecules or atoms making up the solid, are just cheek by jowl, pressed into a very tight, rigid structure that doesn't really expand and contract much, and the particles that make up the matter are not free to slide past each other. In a liquid, you have a little more uh, vibrational and rotational freedom for these molecules, these particles that make up matter. They can slide by each other. The liquid can actually not expand, but can change its shape to reach a constant level in its container. And of course, in a gas, the particles are well separated and in constant motion. Gases expand to fill their container. We just got done talking about gases. The reason I'll come back to this cartoon is it's really important to focus on. We are going to start this module by talking about intermolecular forces and their relationship to observable properties of chemicals like boiling point and melting point. It's really important to remember that for a change in this unit, in this chapter, we're going to be talking about the chemistry of what we call physical transformations. Liquid water going to gas phase water, solid water going to liquid water, solid CO2 going to gas phase CO2. And so in this chapter, for the first time, we're talking about what chemists call physical processes. Reactions that happen, but they're not chemical reactions. They are physical reactions or a physical process where molecules become more or less separated, or molecules become packed into a different order. At the end of the reaction, not covalent or ionic bonds are broken inside of a molecule, and atoms change partners as a result of chemical reactions. When you talk about liquid freezing and becoming a solid, or a liquid boiling and becoming a gas, you're not breaking covalent bonds, you're not breaking chemical bonds. Instead, what you're overcoming are the attractive forces that act between the particles or act between the molecules, what we call intermolecular forces, or IMFs. And this chapter is largely going to be about not covalent bonds or ionic bonds, but these types of attractions outside molecules, what attracts one molecule to another molecule that's different than covalent bonding, that's different than ionic bonding. And we need to think about it from a different perspective. So recognize, for the first time in this chapter in many ways, we're not going to be doing any chemistry in the sense that when we talk about specific reactions, atoms are not going to be changing partners. Molecules or atoms are just getting farther apart from one another or closer together as a result of a transition from one phase of matter to another. When we talk about a transition from one phase of matter to another, we call that a phase change. Phase changes involve any physical process where we go from one state of matter to another. So if you're talking about water, ice, H2O, solid melting as a result of heat input, that's the delta, that's the triangle here, to form liquid water, that's a phase transition. That's a physical change of water, ice to liquid water. Now, to perform this phase change, we still need to add heat energy. The temperature of the system would need to go up. But nothing's happening to the covalent bonds inside the water molecule. Water, ice, liquid water still have the same chemical formula. All that happens in this physical transformation is that the particles that are the water molecules that were packed tightly together in the solid are a little bit more loosely packed or in a different arrangement in the liquid. And so we're concerned in this chapter for when we put in a small amount of heat energy to push through a phase transition, a solid melting to form a liquid, what's the difference between this solid water ice and this liquid water at a molecular level? Well, it's all down to disorder and arrangement in the particles and how close they are together. To get ice to melt, what we need to do is put in enough energy to overcome the attractive forces between the water molecules and spread them out and disorder them a little more. Same thing if we're boiling water. We have liquid water where the water molecules, the particles are free to slide by one another and they can level off and change their shape a little bit to fill the bottom of a container. We put in more heat energy and we get the water to boil, or from a science standpoint, we would call that vaporize. The liquid becomes a gas, and now the gas particles are much more spread out and they're in random motion compared to the liquid. But it's worth noting that we haven't broken any chemical bonds here. We're just pushing the molecules farther and farther apart. And so you need to build kind of a file structure into your brain where we were talking about physical measurables, boiling point, melting point, viscosity. We're talking about overcoming attractions between molecules. Where we're talking about chemical reactions, we're talking about breaking covalent or ionic bonds inside a molecule or a chemical compound. Even dramatic physical transformations, boiling water, CO2 subliming to form carbon dioxide vapor, these typically don't take a lot of energy, not nearly as much energy as it takes to actually break covalent bonds. So when we talk about physical transformations in this chapter, even more exotic physical transformations like sublimation, we're talking about a small amount of energy input that just results in molecules becoming more disordered. No new covalent bonds forming, no old covalent bonds being broken, no atoms changing partners. We're just loosening kind of the connective tissue between the molecules and allowing them to go from a more ordered phase of matter to a less ordered phase of matter, or vice versa. And ultimately, we're going to take these kind of blunt force rules at the back of the chapter, and we're going to talk about how we can use what we've learned about intermolecular forces, these attractive forces that hold molecules together, to explain important phenomena that are crucial to how life on Earth works. For instance, the fact that water ice, solid water, floats. That means it's less dense than liquid water. And this is a really unusual property for a solid to have. Almost all other solids are more dense than their liquid counterparts. If water ice wasn't less dense than liquid water, life on Earth would be very different because you would have ponds and freshwater bodies freezing from the bottom up. There would be no pocket of water under the ice for living creatures to continue to exist. And it would change a lot about how our ecosystem functions. We can also use, as I mentioned at the beginning of this lecture, what we're going to learn about intermolecular forces to explain things like how a DNA double helix forms and why specific nucleotides, specific bases in the DNA sequence only recognize their counterparts. Adenine specifically recognizes thymine, guanine specifically recognizes cytosine, and that's key to both how your DNA assembles and how your DNA is replicated. So what we learn about intermolecular forces in this chapter also is kind of the introductory step to explaining how important biomolecules like proteins, specifically enzymes, and nucleic acids like DNA and RNA perform their functions in a living organism. So obviously your assigned reading for this chapter is going to be all of chapter 10. So you're going to need to get to grips with the whole of chapter 10. Our big goal here is we want to learn how to connect the chemical structure and the chemical formula of different types of compounds to the types of intermolecular forces that hold the molecule together. And we're going to use what we learn about intermolecular forces to do things like predict the strength of the physical properties of the pure compounds, relative boiling points, relative melting points, and we'll also talk about the fundamental structure of molecules and atoms, particles inside solids and liquids. So we're going to start by learning to identify polar molecules, and then we're going to link the polarity of a molecule to the type of intermolecular forces that it might possess. The more polar a molecule is, the stronger intermolecular forces it will have access to. And as a result, the higher its melting point and boiling points are going to be because the particles are more attracted to each other. So it's going to be a lot of spatial reasoning and going back to what we learned about molecular geometry, electronegativity, bond dipole, and polarity of molecules to start the chapter. Then we're going to take a mathy turn and start going back to kind of gas law stuff, learn how to use the Clausius-Clapeyron equation to calculate a boiling point or a vapor pressure at different temperatures. We're going to talk to you about phase diagrams and how to interpret them. And we're going to end by talking about the crystal structures of important types of solid chemical compounds at typical temperature and atmospheric pressure, or talk about how we can relate things like how silver atoms pack into the crystal structure that represents silver metal, and how we can use the crystal structure of silver metal to make an experimental measurement of how big a silver atom is. So we're going to start with a lot of spatial reasoning, go back and review some of the stuff from our earlier chapters in Gen Chem 1, talking about molecular geometry and how we get a Lewis structure from a chemical formula. We are then going to end by doing a lot more math intensive treatments of solid and liquid structures. And so there's going to be a lot of relevant vocab that we're going to go into. Make sure you get a handle on the vocabulary as soon as possible, because it's going to be, as much as we're always speaking a different language that most humans don't ordinarily speak when we're in a chemistry classroom, when we're in this chapter, we have a whole new range of vocabulary that's going to kind of bridge everyday concepts that we're familiar with properties of molecules that are more difficult to describe. So particularly make a start on recognizing what we mean by polarity in the context of polarity in a bond and polarity in a molecule. You're going to want to know your intermolecular forces and what makes an intermolecular force different than an intra or inside a molecule bond like a covalent bond. And get to know your main intermolecular forces, dispersion forces, ion dipole forces, dipole-dipole forces, and hydrogen bonds. So it's a vocab intensive chapter. Okay, so that was a bit of an intro. I will meet you back here in a few minutes to start talking about polarity of molecules and how that relates to the types of intermolecular forces that hold molecules together in a solid or a liquid.